Good morning, everyone. So this is Dr. Knight with you in ECC 3204, lecture number 5 or chapter 5, but this is going to be part number 2. So part number 2, I want to discuss about the Hamming error correcting code because it might be on your exam and I want you to fully understand what that it is about. For your exam, it will be on 29th November 2022. The time will be from 2:30 p.m. to 3:30 p.m. But please come at least by 2:15 p.m. You are able to come early. If you decide to come at 2 p.m., the door is already open. You can come in. Okay, so what do you need to bring for your exam? You need to bring your pencil or pen and your calculator if needed. Pencil or pen and calculator and anything that goes along with pencils and pens like eraser or ruler, whatever that you need to do your exam neatly. But these are the essentials. Okay, what else? You are not allowed to bring in your phone to the exam. Your bags should be at the back of the hall. So if I catch you having your phone in your hand, I can disqualify you from taking the exam. That's the extreme case. If you forget, please don't forget, if in any case you forget that you have your phone on you, call me so that I can take it from you. And if that is the case, I will keep your phone until the exam is over. But please, do not bring in your phone. If in any case you forget, call me so I can take your phone. Because if I have doubts that you are attempting to cheat on this exam, I will need to fail you. Okay? Alright. So this is test number 1 and this will be applied for test number 2 and also for your final exam as well. Alright, so let's continue. I want to discuss about the Hamming error correcting code. Okay, so we have seen this slide before. If you still remember what we talked about. So basically, I have 4 data bits that I am assigning inside these inner circles, right? These are the data bits. And outside this circle would be the parity bit. Now, for this particular example, the parity bits, let me write that down. The parity bits should make the number of ones to be even. And this depends on the criteria that you want to set. Maybe you want the parity bits to be odd. Maybe you want the parity bits to be a number of ones to be even. Sometimes you want the number of zeros to be even. So it depends on the criteria. So for this particular example, the parity bits should make the number of ones in a circle to be even. Okay, so now we try to assign the parity bits and see if we got it. So for this circle A, we have 1, 1, 1. So this is odd. We need another one to make it even. For circle B, we have 1, 1, 0. This is already even. So I'm going to assign this as 0 because I don't want to make this odd. And then for circle C, we have 1, 1, 0. So this is already even. So I'm going to assign this as 0. So you can see here in part B or in figure B that this is exactly what they have assigned. It is exactly the same. Okay, so the parity bits function as our check bits. So in this case, you would have 4 data bits and you have 3 parity bits, or you can call it as check bits. Let's imagine a scenario where I am transmitting these data bits over a communication line. So I have 1, 1, 0, 0 over here inside the circle and my parity bits are 1, 0, 0. So if I want to determine whether my signal is actually correct or my data bit is actually correct, I would go for the parity bit and check if it checks out, right? So for circle A, I am seeing 1, 1, 0, 1. But so this is an odd. but I already know that the criteria for my circle should have even ones. So this is obviously something is wrong in circle A. Now let's check circle B. So circle B has 2 ones, which makes it even. So this seems correct. So now we check for circle C, and circle C also is an odd. So I know that between A and C circle, there is something wrong somewhere, right? So the part that overlaps with A and C is only this guy. Is only this guy. Oh, sorry, this is with B. The only part, the overlap between A and C only occurs in this region. For this region, it is already part of B. So here I already know, oh, okay, so this data bit is not correct because when it is a 0 over here, it's making my circle odds. So what happens if I were to change this to 1? I would have even number of ones, and for the circle C, I would have even number of ones. So this is how the parity bit functions. You get to check whether it fulfills the criteria that you have set earlier on. So now that you know that this is problematic, you would change this and correct your data bits. Okay. So hopefully everyone understood that. Now we are going for a slightly harder problem. So we have seen the Hamming code applied in the form of Venn diagrams to help us better understand how it works. Now this illustrates, this figure 5.7 illustrates the process of how that happens. So if we were to apply what we saw just now, we have seen that the M was 4 data bits. Let me just try to write that down first. And then we saw that we had K parity bits of 3 parity bits. Or we can just call this as check bits. So I'm just going to write 3 bits over here. So how do I know if I have 4 data bits, I need to have K equals to 3? So basically there is an equation that tells us how many check bits do we need for a certain number of data bits. So the equation is, let me try to write that down. It is 2 to the K minus 1 is greater than M plus K. Now let's see. Let's try to apply 4 data bits where M is the data bit, and we want to know how many check bits is necessary to do the error correcting code. Okay. So let's say I try to apply this as 2 check bits minus 1, and I want to know what is the equality sign for this. So M would be 4, and if my K check bits would be 2, that would be a 6. So this would be a 6, and 2 to the 2 is 4. 4 minus 1 is equal to 3. This would be a 3 and a 6. So the equality over here would be this way, which is incorrect. So how many bits do I need? So I go another level up, whereby I assign my K as 3. So if I am assigning my K as 3, I should have drawn this somewhere else. Let me try to take this over. Oh, let me try to take these somewhere else. Cut. New slide. Okay, so this is wrong, and let's proceed with, this is K equals to 2, and then we want to test out K equals to 3 parity bits. So this equation would be 2 to the 3 minus 1, this is 8 minus 1, which is a 7, and then we have our M as 4, and we decided that we want to check if K equals to 3 is correct or not, and this is a 7. Now this tells us that it is equal, or it is basically equal, which satisfies this main equation. Now it doesn't stop there. I can also say, can I have 4 check bits? 4 check bits. So this would be 2 to the 4 2 to the 4 minus 1. 2 to the 4 is 16. 16 minus 1 is a 15. And then my m is still 4, and I wanted to know if k equals to 4 would satisfy this, and it does. So this is correct. This is also correct. The minimum number of check bits that I need for 4 data bits would be 3. But I can also have more than 3 because this inequality tells me that the number of check bits should be satisfied by this equation. Okay, so that is how you determine how many check bits you need for a certain number of data bits. Now let's try to figure out another example. So I'm still using this equation. Let's say I have my m equals to a 16. And I want to know what is my k. So using that equation, I need to know what is my k. So this is going to be 16. My k is unknown. I am going to try to put my k as 3 and see what would happen. So 2 to the 3 would be 8. Minus 1. So this is 8 minus 1 is a 7. And my m is 16 data bits, and my k that I have decided for this is 3. So this is obviously wrong because it does not satisfy this inequality that we want. So we need to go further up. K equals to 4. This would be 16 minus 1, which is a 15. And this is still going to be incorrect. What about k equals to 5? 2 to the 5 minus 1. So this would be a 31. And this is obviously going to be bigger than 90. So k equals to 5 is the minimum number of check bits if your data bits is 16 data bits long. Okay? So back to the diagram. Now m is your data bits and k is your check bits. Okay, so how do we store this m plus k? M plus k bits is stored as a word in a memory. So let's try to find out how to form this word. So let's talk about the layout of data bits and check bits in the form of a word. We have seen it in the form of a Venn diagram, but obviously this is not how it is stored. It is data are stored in the form of words. So this is how we want to figure out how the m plus k word bits are formed. Okay, bit word, sorry, m plus k word. So m is the data bit and your k is your check bit. Okay, so let's say I am trying to transmit a certain signal. So my input word excuse me, my input word or my signal is 0, 0, 1, 1, 1, 0, 0, 1. And to make this easier on me, I will label this as D1, D2, D3. I need to stretch this out. Oh, the wrong stretch. Let me try to group this first. Stretch it out. Okay. And then I have my D4 over here, D5, D6, D7, and D8. So your D1 always starts at your rightmost position. Now, this is my M. How do I put in my K? And we have talked about this before, whereby the first position, the check bits would be placed at the position to the power of 2. So this is 2 to the power of 0. This is 2 to the power of 1. This is 2 to the power of 2. And this is 2 to the power of 3. We already know that for 8 check bits, we would require at least 4 check bits. Sorry, for 8 data bits, we would require at least 4 check bits. So here, I am trying to figure out what is the position of my check bits. So here, the check bit position would be 2 to the 0, which is equal to 1, 2 to the 1, which is equal to 2, 2 to the 2, which is equal to the position number 4, 2 to the 3, which is equal to the position of number 8. Now, what about the positions that we have already assigned here? This is the position within the data bit. This is the position within the word, within the entire word. Remember, we are trying to form the M plus K word. So this forms the entire word. So if my C1 is already at position 1, C2 is already at position 2, so my D1 gets to go over here. And then for C4, it gets position 4, and then the rest is empty, so I get to put my D2, D3, D4. And then my C8 is filled at position 8, and then the rest is empty, so I get to fill in my D5, D6, D7, and D8. Now I have 12 positions altogether, which is exactly how it should be, because 8 data bits would require 4 check bits or more. Okay, so now that we have established how they are ordered, I would like to remind you that the bit position can also be translated in the binary form. Now, why is it important to translate the bit position in its binary form? Because we need to do some calculation on how to assign the bits, on assigning the bits for our C1, C2, C4, and C8 later. Okay, so assuming we already know that our input is, this is going to be 1, and this is going to be 0, 0, 1, 1, 1, 0, 0. How did I get this value? I got it from our input word. So what are the value bits for C1, C2, C4, and C8? So let's do that. So let's try to figure out what is the C1 calculated. Okay, so first let's look at the position. The position is 1, and that translates to 0, 0, 0, 1. And this is for C1. So C1 has a value 1 at the rightmost position. C2 has a value 1 at the second rightmost position. C4 has a 1 in the third rightmost position. And C8 has a 1 in the leftmost position. So here, I want you to look at this and see which data bit has the same position of 1s in their position number. So we will try for C1 first. So let's look at D1. Does D1 have a 1 in the rightmost position? Yes, so I will put in D1 over here. And then I go for D2. Does D2 have it? Yes, it does. So I'm going to put D2 over here. Does D3 have it? No. Does D4 have it? Yes. So D4 has a 1 in its rightmost position, and D5, D7 has it too. D5, D7. Now what about C2? So C2, we are talking about the second rightmost position, which is this guy over here. So does D1 have it? It does. So I'm going to write in D1. Does D2 have it? It does not. Does D3 have it? It does. So D3 goes into our equation. And then D4 has it too, goes into our equation. D5 does not have it. D6 has it. D7 and also D8 does not have it. Now you repeat this process for C4 and also C8. So let's try to do this. So C4, third position. Erase everything first. So C4 is third. So I'm going to look at D1. D1 does not have it. D2, yes. And then we have D3, yes. And then we have D4, yes. And then we have, what about D5? No. D6, no. D7, no. And we have D8. Now for C8, C8 is the leftmost position. Let's go for D1 first. D1 does not have it. D2 does not have it, does not have it, does not have it. Yes, 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 yes. So we have D5, D6, D7, and D8. Now this equation, How do we find out what is the bit assigned to these check bits? You need to use the XOR. You need to use the XOR gate to find out. So this is the symbol for XOR. Let me try to write it first. If you still remember what XOR is, I don't know if you do, but let's talk about it. And then we have this guy over here, this one over here. Okay, so how do we perform XOR summation? So if you still remember, so D1 is 1, D2 is 0, D4 is 1, and D5 is 1, and D7 is 0. So if I were to perform XOR function on these data bits, they would give me 1 and 0 would give me a 1, and then a 1 and a 1 would give me a 0. A 0 and a 1 would give me a 1, and a 1 and a 0 would give me, let me try to write that nicely. 1 and a 0 would give me 1. So the check bit assigned for C1 would be 1. So for C2, it is 1 for D1. Then we have D3 as a 0. And then we have a D4, 1. And then we have a D5 as 1. Oh, we don't have a D5. Sorry. We have a D6 and a D7. D6 and a D7. So that is 1 and 0. So 1 and 0 would give me a 1. 1 and 1 would give me a 0. 0 and 1 would give me 0 and 1 would give me a 1, and 1 and 0 would give me a 1. So C2 would be 1 as well. So let's do for C3. Sorry, C4. C4. Okay, C4 is D2, D3, D4, D8. 2, 3, 4. So 0, 0, 1, and 8. That is a 0 over there. 0. Okay, so 0 and 0 will give me 1. 1 and 1 would give me a 1. 0 and 0 would give me a 0. 0 and 1 would give me a 1. And 1 and a 0 would give me a 1. So the check bit assigned to C4 would also be a 1. Now I don't have enough space. Let me try to do it on top. So D5, 6, 7, 8. 1, 1, 0, 0. 1, 1, 0, 0. We're trying to find out what is the check bit assigned to C8. So 1 and 1 would be a 0, 0 and 0 would be a 0, 0 and 0 would also be a 0. So the check bit for C8 is 0. So now I can write it over here. 1, 1, 1, and a 0. So the word for the word that I have from M plus K would be 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1. It is based on these bits that we have found. So that is how you find out how many K bits that you need for a certain length of data bits. That's your first step. And then the second one is finding out what is the bit assigned to these check bits. So best believe that this will be coming out in your exam, might come out. Okay, so hopefully everyone understood this problem. And please try to find some problems similar to this and try it yourself. Okay, so we have discovered that our k check bits is 4 bits long, and we found out that it is 0, 1, 1, 1, which corresponded to the C1, C2, C4, and C8, right? Okay, so when the M plus K is stored in the memory and the memory tries to deliver this data bit, it delivers the M first to a function over here. The function would generate a new K check bit. It would deliver a new check bit. It would generate it from this function to see if whether the memory stored is correct or not. And the new K check bits is going to be compared with the K check bits that we have formed earlier with our word. So let's say this is our original check bit, but for some reason our function generator produced 4 K bits which are 0, 0, 0, 1. Let's say this is what we get. Okay, which is obviously wrong, but the system does not know it yet, the machine does not know it yet unless it tries to compare. Okay, before we try to compare this, let me try to repeat myself here. First of all, we know that we have our 0, 1, 1, 1 as our check bits. This is our K. And for our M, we already know the input word for that. And the M plus K is stored in the memory. When it is time to access this this word in the memory would transfer M and K separately, where K is the check bit and M is the data bit that is stored in the memory. Now we don't know that if M and K is actually correct or not. So what it does is that the M that is accessed from the memory will go through a function generator. The function generator produces a new K. And if the K is similar, let's say the K produces a 0, 1, 1, 1 as well. So when you compare it, it is the same, then you know that your stored word is correct. But if your K is incorrect, what is the information that we can get from this? So let's say our K that we generated using this function based on this word stored in the memory is 0, 0, 0, 1. So trying to find out what information can we extract from this. So this is our original check bit. Okay, let me try to write this somewhere else. Okay, let's move it over here. Oops. Let's move you over here. Okay, so I have some space. So we know that we have our C8, C4, C2, and C1 over here. And our original check bit would be 1, 1, 1, 0. And the K that we got, the new K at least, is, let me try to use a different color for this. It is 1, 0, 0, and 0. Now I still use my XOR function to do this. Let's use purple now. And performing the XOR function, 1 and 1 would give me a 0, 1 and 0 would give me a 1, 1 and 0 would give me a 1, 0 and 0 would give me a 0. So from this comparator, I got this bit value 0, 1, 1, 0, where 0, 1, 1, 0 tells me that this is the 6th position where the error has occurred. And I look back at my input memory and I will correct the 6th position. If it's a 0, I will correct it to a 1. If it's a 1, I will correct it to a 0. So that is the beauty of the error correcting code function. So when we are talking about the 6th position, are we talking about the data bit position or are we talking about the word position? So let's go back. When we're talking about the 6th position, we are talking about this guy over here, which means that what we are receiving is actually a 1 for our data bit 3, when instead it should be a 0. So if we get a 1, we would flip it back to 0 so that our code, so that our word is correct. This is specifically for a single error correcting code. I'm not going to cover the double error correcting code for this class. If you are interested, you can read on that. And that is it for our final part for chapter 5. So I will see you during the exam. Everything is subjective. There will not be any multiple choice questions. You don't have to memorize the history of computers, but the rest is fair game. Alright, all the best. Take care. Bye-bye.